Welcome to Spring LIB.
The answer to chapter 30, problem number 40. Let me correct that. Chapter 30, problem number 40 from the Smith Organic Chemistry textbook. And this problem asks us to draw a stepwise mechanism to go from the starting material that we're given to a steroid molecule. The very first thing to do is probably to redraw this so that the orientation makes a little bit more sense, and so that it's easier to see how these rings are going to close up. So I have redrawn it. I am, as much as possible in this answer, going to abbreviate so that I don't have to redraw this large molecule over and over again. The only reagent that we're told that's being used here is some acid. And so obviously this reaction has to start with something with some acid. So a lone pair of electrons from the oxygen of this alcohol is going to grab a proton from the acid. And so that's the first step. So we can redraw this. So this oxygen now has 2 protons and a positive charge. And so, as I said, I'm just gonna put an R group there, so we know the entire rest of the molecule is there. This way, I don't have to waste a bunch of time redrawing parts of a molecule that are not taking part in this particular step of this reaction. Like I said, this alcohol has been converted to a good leaving group now, so the electrons of this bond will revert to that alcohol, to that now H2O, and so that will leave as water. And so we'll end up here. So we now have a positive charge there, carbocation there. And so basically this carbocation is part of an allylic system. So this can spontaneously rearrange, and it does. And so I suppose we can show that double bond moving, and like I said, it does. And that gets us to here. And now I think we need to draw a little bit more of the molecule because other parts of this molecule are going to be taking part now. So we'll throw the R group there. We'll call everything past there R. So that. And now our carbocation is on that carbon. And what's going to happen now is this double bond can attack that carbocation. And so that's going to form a new bond. And we've closed down the first of the new rings that we have to make now. And so now we have that new 6-membered ring made there. And we can draw some of the rest of this molecule in now. We'll just put the R group there. And of course, we have a carbocation on this carbon now. And so just as in the previous step where we had the electrons of a double bond attacking a carbocation, these electrons can now attack that carbocation. And so that's going to close down our second new ring. So we have our second new ring there. And now I think finally we need to draw the last piece of this molecule that we've been omitting so far. So there's a triple bond. And of course, we have a carbocation here now, resulting from the double bond electrons being used to make a new bond previously. So there's our carbocation. And once again, the same as it's been for the previous two steps, the electrons from this triple bond, so I guess it's a little different. Previously, they were double bonds. So the electrons from this triple bond can attack that carbocation. And so the result is going to be the formation of the last ring that we need to make. So here we go. Here's our ring system. And I guess at the start of this problem, I referred to this as a steroid molecule. And I should go back and say, this is not actually a steroid molecule. I guess I looked at it wrong at first. So if it was a steroid, it would be 3 6-membered rings and 1 5-membered ring. And instead, this is a 5-membered ring, 2 6-membered rings, and then a 5-membered ring. So that's my mistake. I hope I didn't confuse anybody. Right. And so this intermediate is going to have a positive charge there now. And so water is floating around. And so one of the lone pairs on a water oxygen is going to be able to come in and add to that carbocation. And so since the rest of this reaction only concerns the top part of this molecule, I'm going to go back to abbreviating the rest of this molecule because it's a lot of drawing, of things that are not taking part in this reaction at all. So there's the 5-membered ring, and then we'll just do this to show that there are 3 more rings out there that we're not really worried about right now. And so when water comes and adds, and I suppose I should put the methyl group there just to be consistent. So water's come and added to this carbocation, as I said. So now we have that. The oxygen, of course, has a positive charge on it because it has 3 bonds. It's 1 bond too many. And so one of those hydrogens of the water can be plucked away by another water. So here's another water. Lone pair on the water oxygen can take this hydrogen. Those electrons can revert to that oxygen. And so now, and actually I am going to continue this on the next page. So let me make a next page. Right. And so now what we'll have is this. So there's our 5-membered ring. Remember, there are 3 more rings attached out there that we're not worried about because they're not taking part in the rest of this reaction at all. And so what can happen now is there is still acid floating around. So I'm just going to draw this as H+. You can draw it as H3O+. It really doesn't matter. It's the same thing. And so the electrons of this double bond can snag one of those protons that's floating around. And so what will happen then, so 5-membered ring, other rings. So what will happen then is our newly added proton will be here. And we will have a carbocation that's formed at the other carbon that was part of that double bond. And so since there's a carbocation on a carbon that's bound to an oxygen, the lone pair on this oxygen can add in, and we can make a carbonyl. So now we have a carbonyl. The oxygen is going to have a charge on it. So the oxygen is going to have a positive charge from having 3 bonds, but of course water can come to the rescue, as it has several times already in this problem. And one of the oxygen's lone pairs can take that proton. The electrons can revert to that oxygen. And so now we have our final product. And so I am just going to draw this out fully again, just because it's the final product. So the whole molecule looks like this. And then there's our ketone that we just made. Right, and so that's it. And that's the mechanism for this reaction. So again, remember, it's really just a series of sequential double bonds attacking carbocations. And then at the end, water attacking a carbocation. And then once that's happened, really just playing with oxidation states to get from the water that attacked to the ketone here at the end. And so again, that's the answer to chapter 30, problem number 40.